Dear listener, today we talk about black holes. So please listen carefully start to end. Understanding light cones, relativity, and black holes in simple terms. Introduction. The universe follows strict physical laws that govern the movement of everything, including light. One of the most important concepts in modern physics is the light cone, which helps us understand the nature of time, space, and causality. By studying light cones, we can explore the foundations of relativity and how gravity bends space and time. The most extreme example of this bending is a black hole, a region of space where nothing can escape, not even light. What is a light cone? To understand light cones, let us imagine lighting a candle in a completely dark room. The light spreads outward in all directions, forming an expanding sphere. This sphere represents how light travels over time. If we look at this process step by step and stack these expanding spheres over time, they form a cone-like shape. This is called a light cone. A light cone shows us what events we can influence and what events can influence us. Since nothing moves faster than light, anything outside our light cone is unreachable until its light reaches us. This concept helps explain why certain events in the universe appear at specific times. For example, if a distant star explodes, we won't see it immediately. Its light has to travel through space to reach Earth. The role of relativity. Einstein's theory of relativity tells us that space and time are connected, forming a structure known as space-time. In space, we can move in any direction, but in time, we always move forward. Light cones show this distinction clearly. While we can freely move around within space, we cannot move backward in time. Gravity, which comes from massive objects like planets and stars, bends space-time. This bending means that light and other objects follow curved paths rather than straight lines. The stronger the gravity, the more space-time curves. This effect is noticeable near very massive objects, like the Sun, where even light bends as it passes by. Imagine lighting a candle. The candle emits a flash of light that travels in all directions, forming a bubble that grows. This bubble is in 3 dimensions and surrounds us completely. If we are inside this bubble, it is impossible to get out of it because we would have to exceed the speed of light. Imagine that we only perceive a 2D slice of space. The bubble forms a circle that grows all around us. If we decompose the situation, image by image, and if we stack the images one after the other, we can construct a diagram in which the bubble of light, which grows over time, forms a cone. This cone widens from the past to the future. And inside of it, we trace a trajectory through time. The sides of the cone are tilted at 45 degrees because for any given amount of time, light always travels a set distance. In 1 year, light will always travel a distance of 1 light year through space. This type of object is called a light cone. As time passes, the cone expands at the speed of light. And whatever we do, our path remains bounded by it. It's impossible to escape it. In relativity, these light cones are essential to understand the structure of the universe. In particular, they restrict cause and effect relationships. To understand, imagine an event that occurs far from Earth, such as a supernova explosion. This event won't be able to affect us until its light cone has reached Earth. Before that, no information about the explosion can reach us, since nothing can be transmitted faster than light. This explosion can only be seen and felt on Earth as soon as we enter its light cone. Causality, the fact that one event can trigger another, is limited by the speed of light. More importantly, light cones allow us to understand the profound difference between the notions of time and space. What is the difference between time and space? Through space, we can move in any direction, turn around, or trace a path that loops back on itself. But through time, all objects are forced to move in the same direction. In time, it is impossible to turn back. We always move from the past towards the future. Light cones allow us to clearly see this difference. Through space, we are free to choose any direction. But through time, the successive light cones force us to always move forwards. We cannot turn around because we are bound to remain within these light cones. This property allows us to define rather rigorously what we call time. Time in relativity is simply the direction in which the light cones are oriented. It is this direction along which we cannot turn back, the direction towards which all allow trajectories point, and in which our future necessarily lies. Space, on the other hand, is the set of all other directions, perpendicular to time. In an area where the universe is empty with no gravity, its structure space-time is straight. Time and space form a symmetric rectilinear grid and the light cones are all aligned in the same direction. We can thus define time globally. In this diagram, time goes from left to right. But imagine now that the universe contains a very massive body, for instance the Earth. If we drop an apple, the apple will gradually fall downwards, deflected by the gravity of the planet. However, gravity affects not only matter, but also light. If the apple emits bubbles of light over time, they will also be drawn downwards. Close to a massive body, the light cones are no longer aligned with each other. They curve more and more, bent by gravity. Near a massive body, the direction of the light cones curves. And in other words, time is bent towards the center of the planet. If the apple falls, although it was motionless at first, it is because its future points downwards. Mass distorts the geometry of the universe, space and time become relative, their orientation depending on where we are. This is general relativity. The more massive a body, the more it bends space-time. But imagine a massive object that is very compact. Such a body would generate a curvature so strong that below a certain altitude all light cones would be completely oriented downwards. If we were to light a candle in this place, all light rays, whatever their direction, would be destined to fall towards the center. This is what we call a black hole. A black hole is a spherical region of the universe, a source of bubble in which the curvature of space-time drives all objects towards the center. If we consider a 2D slice of space, the black hole manifests as a circle which stays static and traces a cylinder through space-time. The boundary of the black hole is called the horizon. Above the horizon, some light rays can escape. But below the horizon, all light is captured. In a black hole, light cones force the path of any object downwards. Time itself points towards the center of the black hole. To understand what a black hole really is, it is wise to consider two different points of view. That of an astronaut who falls into the black hole, and that of a distant observer stationed at a great distance. What is a black hole? A black hole is formed when a massive star collapses under its own gravity, creating a region where space-time is so curved that nothing, not even light, can escape. The boundary around this region is called the event horizon. Anything that crosses the event horizon is trapped and will inevitably fall to the center of the black hole, known as the singularity. From an outsider's perspective, objects falling into a black hole appear to slow down and never fully disappear because light from them takes longer to reach us. However, for someone falling into a black hole, time and space behave differently. They would experience time normally but would be pulled toward the singularity without any chance of escape. How black holes affect space and time. A black hole dramatically alters the shape of space-time. Close to a black hole, light cones tilt inward, showing that everything is pulled toward the center. This means that within the event horizon, the future always leads to the singularity. No force in the universe can stop this from happening. Even outside a black hole, its presence bends light and warps time. Scientists have observed that clocks near strong gravitational fields run slower than clocks farther away. This effect, called gravitational time dilation, has been confirmed using precise atomic clocks on Earth and in space. The significance of black holes in the universe. Black holes are not just theoretical objects, they play an important role in the cosmos. Many galaxies, including our own Milky Way, have supermassive black holes at their centers. These black holes influence the motion of stars and even help shape galaxies. Scientists study black holes using telescopes that detect X-rays and radio waves emitted by material falling into them. One of the most famous discoveries in recent years was the first ever image of a black hole, taken by the Event Horizon Telescope in 2019. This image showed the shadow of a black hole surrounded by glowing gas, confirming many predictions made by Einstein's theory. Conclusion: light cones help us understand the nature of time and space, showing us what is possible within the limits of the universe's speed limit, the speed of light. Relativity explains how gravity bends space-time, and black holes are the ultimate example of this bending, where time and space become so distorted that escape is impossible. Studying black holes gives us insights into the fundamental laws of physics and the structure of the universe. While they may seem mysterious, black holes follow the same principles that govern everything else in the cosmos. By continuing to explore them, we deepen our understanding of space, time, and the universe itself. Please like, share and subscribe my channel. Thanks.